Okay, can you hear me?
Yes. Go ahead.
Okay. Hello. Today I'll share the paper. The title is wait, change. The title is Oxidized Iron in Garnets from the Mantle Transition Zone. First, I'll introduce the author. This is the first author, the Kate Kiseeva. And Kate Kiseeva got her PhD degree in experimental petrology at the Australian National University. And then she worked as a postdoctoral researcher in the University of Oxford. And since the 2018, Kate has been a lecturer at the University College Cork. And she focused on the mineralogy, isotopical chemistry, and the oxidation state of the Earth's mantle, etc. And then, before we start, I want to introduce some background about this paper.
Lei,
Yeah.
sorry, could you move
Yeah.
to the front page? The
Yeah.
very first one. Yeah, maybe I could explain more about the authors. So here, to me, that there are three group of people. So one group of people, there are, of course, Kate and her postdoctoral advisor, Bernie Wood, which is a third work author, the fast word. So this group of experimental petrology people that has a really good concepts on petrology, because after all, this is a petrology question. On the redox of the Earth mantle transition zone, and they give a natural sample evidence. And then I don't know where the samples are really coming from, but there are two people listening here where they have been working on natural diamonds for decades. One is Thomas Stahl, here as the first author in the second row of the author list, and also Jeff Harris, the third row, the first author of the third row. So for them, that they have been working on the deep diamond for a while, or all diamond inclusions for decades. So I suppose that's where they get the samples. I'm not sure though, but I think it's likely. We'll have a lot of collaboration. Another third group of people, there are many people from Bayreuth, BGI from Germany, and these are the people that they are specialized in different types of the analytical instrument for the ferric iron analysis, from Zen's to most power analysis, especially most power analysis. So Catherine McCammon, the person in the fourth author of this paper, the name on the right in the first row, Catherine McCammon. So she's expert on that most box analysis at the BGI. And actually another person that also on BGI is the very last author, is the Leonid Dorovinsky. So he was from Russia before. So yeah, he's expert in the time animal cell. So basically, it's a little bit multidisciplinary research to investigate the question. So there are three group of people from experimental petrology from the natural diamonds, as well as for the ferric iron analysis people. Okay. So like I also Kate, she made her name in the sulfide research, including the partition coefficients of all types of elements in sulfides, between sulfide silicates, with application to Earth's mantle and earlier process a little bit, and also for diamonds, another group of discipline research direction that has been pursuing in recent years. I think probably on Wednesday she's going to present some of work that is not published yet, but I think it's probably going to publish on the way. I don't know what it is, but it's likely to be something on diamond too. So we can hear more about some published work on Wednesday. But we can first review what Kate has been doing in the recent years for this publication as well as another one like could briefly talk about. Okay, so go ahead. Please move to the third page and continue with your leading the paper discussion.
Okay, I'll continue. This paper discusses the oxygen fugacity, which is fundamental thermodynamic parameter in the growth and the stability of the mineral phases from the Earth's mantle. And the previous study established the modeling of the experimental data indicates that at approximately 8 JPa, mantle FO2 will be 5 log units below the FMQ and at the level where the nickel and iron metal became stable. And we know the iron is the dominant malevolent element in the Earth's mantle. The disproportionation of the Fe2 plus plays an important role in determining the oxidation state like this equation. However, the oxidation has not been characterized in the samples from the lowermost up mantle or the transition zone. And as for the evaluation of the oxygen scarcity conditions in the deep earth, maybe not the natural mineral associations as the great value, but they are very real. So there's no doubt that diamonds are the excellent samples for the probing the information about the Earth interior. And look at this figure. We know the most diamonds are coming from the lithosphere, and some diamonds are coming from the sublithosphere, and the few diamonds are coming from the lower mantle. But no matter, as for those diamonds are very important for us to explore the oxygen scarcity of the Earth's interior. So in this paper, the author used the meteoritic garnet inclusions in diamond coming from the transition zone as the target to study to research the oxygen scarcity of the transition zone. I think there are main two reasons for choosing the garnet as a research object. Following the two reasons. The first reason is at the pressure beyond the 7.5 GPa coexisting pyroxene dissolves into the garnet as a meteoritic component. And excess silicon is a consequence of the increased solubility of pyroxene components into garnet with increasing pressure. And second reason is garnet is a key host for the Fe3 plus in the up mantle, and it's important to determine how the Fe3 plus contents and oxygen scarcity. So the author wants to use to determine how the oxidation state of iron garnet, including diamond, from the up varies as function of depth and to translate measured oxygen state to the oxygen scarcity. And there are some methods about this paper.
Hold on, Alex. I could add a little bit more to this discussion. So for this one, actually, Leah, I think you might mention about one paper that actually after this one, also cited in your 2022 GC paper. So that's so maybe you can move back to the previous slide. So yeah, the previous slide with the equation. Yeah, okay, we can look at this equation. So in upper mantle, you have the iron 2 plus locates in the resides in the olivine, also some in the pyroxene too. And then in the upper mantle, iron metal is absent. Most of the upper mantle is iron metal is absent. So you have some other iron 3 plus resides in garnet, or some actually in CBX, OPX, but they're relatively but their reach are relatively low. Actually, we should need to revisit that. But the upper mantle is a spinel and a garnet that holds a lot of ferric iron. And then with the increased pressure, of course, the experimental petrologist shows that more and more iron 3 plus incorporated into garnet. And then until at some point, if we start with assuming how much about iron 2 plus in Earth upper mantle, for example, we have about 7% of iron, total iron in upper mantle, and among them you may have about let's say 0.1 of that. So basically, you may have like 0.7% of iron 3 plus, and then you have like say 6.3% of iron 2 plus. in the Earth's upper mantle. That's where we got our samples as upper mantle pyrrolite composition, for example. And then people measure the how much iron 3 plus could incorporate into garnet. Over the decades, people find that, okay, the garnet could host a lot of ferric iron. So you consider the mass fraction of the garnet in Earth's deep upper mantle or transition zone, then the garnet could carries all the iron 3 plus, as we mentioned earlier, that if we assume the upper mantle has 10% of the iron is an iron 3 plus, then you may have around like 0.78% of iron as an iron 3 plus. Then people show that, okay, by the garnet in the deep upper mantle transition zone, they can host all the iron 3 plus and even more than the pyrrolite. Then that causes a problem because you don't have enough iron Fe3 plus. Then you need to force this reaction to move from the left to the right, and therefore you generate enough iron 3 plus and for the garnet, but at the same time you need to precipitate the iron FeO, Fe metal, native iron, elemental iron to equilibrate in the system. So of course, when elemental iron is present, the condition is very, very reduced. So that's how people came into this. And so the paper is sent in the chat. So for the Bayer, in their study, they showed that the garnet doesn't always host more iron 3 plus with increased pressure. So then they bend. So then they increase and then decrease a little bit. So that will cause some change when we calculate oxygen gas in the Earth transition zone. So, but this Bayer's work, of course, is assuming a more ideal bulk metal condition. So for Kiseeva's work, that they are going to they could access some deep diamonds. People know approximately the depth of where they're from according to other stability of other high pressure minerals, and then you analyze the garnet Fe3 plus content. So basically provide the natural sample evidence for the Earth's mantle transition zone oxygen fugacity. Of course, as mentioned earlier, so the Bayer's work, they use the pyrrolite composition where they assume something like that, or you assume a subductive slab composition, which is different than the pyrrolite, of course. And for the natural samples, we won't expect the deep diamonds sample the pyrrolite. Like deep diamonds, when they precipitate, they form in some very unique conditions. So in this case, basically, Kiseeva 2018 Nature Science paper later on, they also argue about that, basically showing that they are interpreted with a very high, very oxidized conditions is caused by the carbonated reaction. So partly because of that, because for deep diamonds, what you sample, you hope you're going to sample the pyrrolite composition, but it's not. You don't always sample that because your formation of deep diamonds is a very special condition. So you won't be able to get the average, but still you could provide insights to people about the transition zone because they are coming from the transition zone. Okay, I've been talking a bit too much. Please move on.
Okay. About their method. The garnet inclusion, so first about the samples, the garnet inclusion in diamond from the Jaggers 14 kimberlite in the South Africa. And about the size, we look at this photo. The left figure is peroxide mount with garnet inclusions, and the red circle as inclusion, and the size are about 60 micron in diameter. And then the right image shows us one of the inclusion under the higher magnification. And then the authors use the synchrotron Musbar source spectral and the single crystal XRD to measure the oxidation state of the iron in garnet. This is about their method. And there are some results. We look at these figures. This figure shows us the ferric ferric contents of the meteorite garnets from the Jaeger's 14 diagram compared with the lithosphere, which this with lithosphere garnets from the peridotite xenolith, and the y-axis x-axis is the pressure calculated by previous barometer, and the y-axis is the Fe3 plus versus total N. And we can, and the red circle, this red circle are the data from this paper, and those points are come from the reference. This is very garnets data, and from this figure we can see this trend. The figure shows the Fe3 plus versus total N is well correlated with the calculated pressure increasing from this point, increasing from with from the 0.08 at nearly 8 GPa, and choose a value between the nearly the 0.3 at 16 GPa and near the 18 GPa this point. There's an increase with the dips in the oxidation state of the iron in garnet, and we can look the y-axis, those points from the transition zone. We can see the iron from the transition zone garnet is at least twice as oxidized as in the garnet from the lithospheric metal. This is about this figure, and then we look this figure. This figure x-axis is pressure and y-axis is log FO2 relative IW buffer. Simply the red circle are from this study, but the blue points are the garnet crystallized coexistence with the iron metal, and we can see 1, 2, 3, 4. Those 4 of the 5 experiments gave the calculated oxygen fugacity, and below this line, the IW buffer. However, the red circle they analyzed in this paper, the garnet only this one point below the FeO equilibrium, and others are all above on this IW buffer. So this implies those points are not equilibrium with the iron metal and not oxidized by the disproportion of the Fe2 plus to the ferrous ion and the 0 ion. Then they propose this line. We can see this line is the carbonate diamond equilibration corresponding to this equation, and we can see the red circle points inclusions are in the diamond stability field, and their approach to the EMOD with the increase in the pressure, which means that the oxidation of the Fe2 plus during the reduction of the carbonate in the field or the melt phases is a mechanism for the generating the Fe3 plus present in the garnet. Then we got the following conclusion. The first is in the upper mantle and the transition zone, there is an increase with dip in the oxidation state of iron. And second is the ferric ion contents corresponds to the oxygen fugacity below the IW buffer, which means that the high Fe3 plus contents were not generated by the disproportionation of the Fe2 plus to the Fe3 plus and iron metal. With increasing depths, relative oxygen fugacity increase and approach to the carbon-carbonate equilibration, suggesting that carbonate was the oxidation agent responsible for the generating the high Fe3 plus of these mantle garnets. And besides, we also read the Kiseeva et al. In 2015 published in the EPS Earth Research, and they test the iron contents of the ferropyroclast inclusions in diamonds from the lower mantle, and this is their result. And from this figure show us the oxygen fugacity values for the mantle ferropyroclast compared with those green lines with the value for the garnet from the upper mantle. Okay, we can see the 1, 2, 3, those three different places garnets from the lower mantle show us their delta log FO2 are all above the IW buffer. This dashed line is IW buffer line. So they are all above this line. And demonstrating the high oxidation conditions with the lower mantle. And we can see those green line and the blue line are very similar. So this similar between the lower and the upper mantle, lower mantle and upper mantle redox conditions for the whole mantle convection. Then I want to discuss the redox condition of the diamond formation. In 2016, Smith actually they find the carbide and alloy inclusion in diamond. Look at this for this picture. So they thought they researched the diamond grew from the reduced iron research liquids in the transition to all lower mantle. So the low oxygen fugacity condition may also exist within the lower mantle. But in this paper, the higher ferric ion contents of the meteorite inclusions in diamonds suggest that those diamonds grew from the oxidized carbonate rich melt or field sourced from the transition zone. So we take those research together. Those studies suggest that the sublated sphere diamond grew under the variety of different redox conditions. And this about my presentation.
Okay, thank you, Lei. But could you also explain the Moosbauer methods in terms of the fundamentals? So how does Moosbauer, what's the principles of Moosbauer, how does it work to measure the ferro iron content for garnet? Maybe not only for garnet, but for all minerals. They have some fundamentals for that. Could you explain to people?
Actually, I'm not very know about the Moosbauer's spectrum. But I think it's I think the Moosbauer's wait, okay, this. I think they calculated the area of the of the peak and different aerial response response the N 3 plus and the N 2 plus, so they can calculate the area to get the proportion of the N3 plus. But I don't know the exactly details.
Okay. I think this is something that we always need to show paper reading. I think it is helpful for our participants to know some principles of the methods, because basically this analytical chemistry, either people analyze stable isotopes or different valence states using Morse power or electron microprobe. I suggest that in the future for paper reading, people at least give a very brief introduction of the methods. Maybe you don't know all the details, but it's okay. But at least you could tell the principles, physics or chemistry principles for that analytical methods, and what type of instrument do they use, and how does the instrument really work. I think that could help. So maybe Umi, maybe you could help us explain this figure in terms of horizontal vertical axis and how Morse power works. Umi? Umi?
Here.
Yeah, I cannot hear you. You're not audible yet.
Hello, am I audible?
Oh yeah. Now we can hear you. Yeah. Go ahead. Go ahead. Please educate us in this reading group about Morse power fundamentals, and also what does it mean in the horizontal vertical axis, and how people fit the peak and then calculate the ferric iron content.
I am not exactly clear. I don't remember it clearly. I have to actually refresh it once. But what I remember is 57 cobalt is used as the source of 57 iron. So basically, it provides an excited state of 57 iron, and then when it comes back to the ground state, there is there are certain kind of emissions that would give the Mosbar effect. So I don't remember the exact details, but this area is calculated. So Fe3 plus will give a particular area, and Fe2 plus will give another area, and then their ratio is like their factor is multiplied with the recoil free factor, and then the ratio is used to calculate the velocity. I don't actually remember it clearly. Maybe I have to refresh it once again.
Okay. Thank you, Umi. So what does the horizontal axis mean here in terms of velocity? Is the velocity of what? Is it the velocity of cobalt 57?
I think it is the velocity of the radiation or the.
Okay. Basically, let's use the cobalt source, I suppose, because they have a cobalt 57 as a source to radiate the samples. They also dope the sample. I think that do they really dope the sample with 57, or do they, let's say, just generate the 57 from the natural samples? I don't know whether they have to do some doping for that. Maybe you know something on this.
The cobalt 57 is like no, it is an artificial cobalt 50, like it's a lab made thing.
Yeah, I know. Cobalt 57 is laboratory one, but for the iron 57, that in the sample that they generate, the gamma rays, in order which is sensitive to the valence state of the iron. So I don't know whether that iron 57 comes from the natural sample itself directly, or does it come from the, also people do some doping on it. I don't know. Because sometimes that, yeah, for measurement, people do something like that. I'm not sure.
Yeah, hello, Umi.
Yeah.
I haven't used this method before, but I wonder, uh, uh, the as for this paper, they use the synchrotron because the garnet size are very small, and do you know the common the common Mossbauer spectral, what's the sample size required?
Mosby requires a little larger sample size, but I'm not sure about exactly the measurement. But it requires larger sample size than the other methods like Zane's, etc.
Yeah, I don't know exactly the size, but it should have, if my recollections right, that needs probably the sample size if the silica is in the size of several millimeters. So you need the samples at least several millimeters to be able to do the Mossbauer analysis. A normal one. But of course, when you go to synchrotron, basically, of course, I don't think the garnets are that big. I suppose that in the earlier figures it show you probably in the size of 0.1 millimeter or 100 microns or something like that. So definitely that is not the size that is measurable by the normal Mossbauer that sits at home in different laboratories. So that's why that they go for the control analysis, which is challenging too. Okay, Liu Linhan, do you know something about this? Because your advisor knows all the details.
Sorry, I'm not familiar with Mossbauer too. Yeah, I didn't do any tests about this method.
Okay. No problem. I think for this, that is something that's, let's say, is common in analytical chemistry, is that, okay, now you have a certain principle that how you are going to differentiate these two valence states in this case. And then these two states are sensitive to different gamma radiation caused by iron 57. And then you basically use source cobalt 57 to radiate it. So that's the basic principle of doing that. Of course, then when people build different instruments, people have different instrument to deal with the sample size or deal with sensitivity. From the synchrotron to the laboratory, to a common laboratory one, but also people need to use standards. So here, actually, so Lei, could you show us that what's the, maybe we can look at the figure captions. They have some, you see that in the figure, they have some yellow parts and they have some blue part. Of course, all the red line, red curve, I think they are showing here corresponds to the fitting result because they have all the dark places are the dots, and also the pink curves are the background. And dark dots, that's the raw data people collected. And then I think that's for the red curve, that's what they get. But I don't know what that's this blue, like greenish, green blue one. I think that's understandable. Basically, we have these two big peak. So that's that bluish green response. Okay, so basically the orange ones depends on their different site. So they basically has X site ferric iron and the Y side ferric iron in the garnet. Okay, so they must have some standards in doing. So like all analytic chemistry, the standards are very important. I think in this case too. And then they have the green doublet in C with smaller splitting correspond iron 2 plus in the clinopyroxene. So they also use another clinopyroxene, basically as a secondary standard, I suppose. Okay.
Yes, about I want to say about the test of the Fe3 plus. Normally they use the Mossbauer and the flag method by the EPMA, and maybe flag method in our country are more more, and but the moss bar in our country is not very normally.
It's more challenging to manage a moss power spectral laboratory. So in China, there's University of Hong Kong has one, but there is not many in the world. I mean, University of Minnesota hosts one, and also for Bayreuth University BGI, that's where they're collaborating. Come from Catherine McCammon for many years. That was one. Actually, there are not many in the whole world that could keep the moss power spectra running. It's big, it's a little bit expensive, and it's hard to maintain. I mean, all of the coils inside is a little bit difficult because the reason why University of Minnesota has it, not because of the geochemists like us that wants that, is the group of people that they are interested in magnetism. So basically, they have this because they have all kinds of they care about the spin state, for example, of different iron and different minerals. So they are really looking for that. So it's those group of people that maintain this kind of instrument rather than most geochemists who mainly use the mass spectrometer. That is more common around the world. But for this, it's a very small community. That's why that's really hard to do this. And actually, let's also explain part of the reason why when we are predicting the ferrous iron content in the samples is very valuable, because there are only very limited number of laboratories in the world that could produce high quality moss power analysis, where most of the samples we just don't know, have no idea how much iron 3 plus there is in those samples, because when we measure by electron microprobe or other weather chemistry, you just know the total. Well, I mean, in the bulk, maybe sometimes you can also get the weather chemistry method to know the ferric 3 plus and ferric iron 2 plus ratios, but you need a really large sample size. But from up to the mineral scale, then it's very hard. But the mineral, depending on the iron, locates on different sites. Basically, there are certain other thermodynamic equilibrium. As I sent another paper in the chat, which is very classic paper by Danfros and Mike Common about the mantle redox. Basically, tells all the story of mantle redox. And you can see there are many chemical equations that listed involving iron as a different state. So for all those equations, basically thermodynamic equations, basically you can look at the different element concentrations, they equilibrate with each other. So for those reactions, if we know those reactions really, really well, basically we don't need to. I won't say we don't need to. I would say we could directly calculate the ferrous iron content based on the concentration of other elements. So actually, that's the initiative that we started doing a lot of projects here in our group. That we think that this thermodynamic equations could be solved, but not be solved by what listed in the Frost and McCammon paper, including the parameters they provided or people provided so far. We think that those equations that have much more complicated thermodynamic correlations among the different element concentrations, and therefore likely machine learning's approach to reveal that very, very complex correlations, which we do believe there is a correlation for the ferrous iron 3 plus concentration with the concentration of all the other elements, including iron 3 plus, iron 2 plus, aluminum oxide content, silicon dioxide content, MgO content, calcium oxide content, etc. So we think that those are correlated thermodynamically, and that's the reason that we were doing a lot of the calculations in that direction in our group so far, not only in the Huang Weihua's 2022 American Mineralogist paper about the ferrous iron content in plasma pyroxene, but also in the coming work that we have been working on, like what the Wumi is working on. Basically, I think that's some of the initiative that we have. That we also apply the same thing to deep diamonds, because Lei has already collected the concentration of different elements in the diamond inclusions, in different diamond inclusions. Basically, we can also use the machine learning algorithm we trained. Basically, we could recalculate a lot of the ferrous iron content, and then we'll come back to plot those samples to see whether they are, let's say, consistent or the same as they as this paper directly measured. So we compare the model prediction with the measurement, but we'll also look at the model prediction at the global scale. Okay, I've been talking a little too much. Maybe for other participants, do you have questions or comments or something? Feel free to open your mic or type.
I have something to say. Actually, I think this all those results are established on the accuracy of the FE3 plus, such as the Moosbauer spectral result. And besides that, in this paper, the author used the previous gel barometer in 2018. I forgot which year. But in to calculate the pressure, the garnet coming from, and in the last year we read the Thompson's this paper also established the gel barometer of about the meteorite garnet. I think if we use this gel barometer result, maybe the result have a more accuracy. And this paper we read before, they're using the machine learning and improves the accuracy of the calculated pressure. I think so. And besides, there are only they test the 30 inclusions in diamond, those red circles, and only 1, 2, 3, 4, only 4 points located in the transition zone. And I think it's difficult to test the inclusion in diamond, especially for those very micro size diamond size inclusions. So maybe that, but this work is a license for us to explore the oxygen scarcity of the deep mantle. I think so.
Okay, that's good. Any other comments or ideas? So Wumi, have you tried for the samples using a Thomson machine learning barometer? As well, so that when you predict the global samples, I don't know whether you incorporated this ones.
No, this paper has not been used because I don't think this data is there in the GeoRock database. But I think the Thomson pressure equation can be used in this case because the equation that they have used for this particular pressure calculation, so in that equation, they have assumed that pyroxene is in equilibrium. However, they did not find pyroxene along with the garnet inclusion. So that approximation is not there in the Thomson machine learning model. So I think maybe Thomson machine learning model will be a better fit to calculate the pressure in this case. So
I think Wumi, you can try it. Yeah, please try it in the coming weeks.
Yeah. Yes, I can take the data, the EPMA data, and I can.
So what's the difference? So Ben has a question that was the difference between Moosbauer and SIMS. So for SIMS, it could not measure ferric iron. So for SIMS, basically it's a mass spectrometer. So they use the ion source to heat the samples and then ionize the sample surface, maybe 1 micron, something like that. And then your sample surface that being ionized by the ion source, then you go fly into the spectrometer. And then by spectrometer, then basically you use the different I would say there's a charge mass ratio, then you differentiate that, and then you go into the magnetic field, which separate them into different channels. Then you have the Faraday cup in the end that will collect to count how many of those particles are hidden in the Faraday cup. But the problem is that for that you are not sensitive to the ferric iron or ferrous iron. So I would say that is something interesting, because if people do iron isotope analysis, I'm pretty sure that there is a strong correlation or a strong difference in terms of the samples with a higher iron 3+ ratio and with a different iron 57 and iron 56 isotopic ratio. So, but I don't know whether those correlations, how well they're very accurately established, because for SIMS analysis, it could basically, if it has all the standards, they could measure the iron 57, iron 56, but how you're going to calculate those to the iron 3+, iron 2+, I don't know. I don't know. Maybe it's a good science question. Could leave it for people to test out. But for SIMS, they cannot directly gets to the valence state. But for Morse power, it can, because the spectra of the Morse power basically is a direct reflection of the different valence state, not only into the iron, but the different other elements, because the basic physics principles are different. So that's why I asked Lei to showing that part. I'll encourage people in the future paper reading, when we talk about before talk about the results, let's very briefly review the methods. So basically some, I would say university level chemistry, university level physics that we forgot, but I think it's good for us to review it again and again, so that we could be clearly sharp on what the principal methods are. We don't have to be experts on that, but at least we should know their principles, how it works, and what is pros and cons. Yeah, and the availability of those instruments around the world is another thing that we could discuss. Okay, so some other questions or comments from our participants today? Okay, that's so much for the discussion today. Let's wait for a speaker to talk on Wednesday. I just very bold guess. I have no idea what the speaker is going to talk about. For diamonds, about the coming work, it's just a random guess for me. I think it might be possible they continue to work on this. Garnets, for example, they just use laser ablation to analyze the trace elements for this garnets. For example, exactly the same paper. I think that could independently become another paper, or people collecting enough diamond inclusion basically could analyze all kinds of isotopes if people are interested in. So once you have natural diamonds, there are a lot of things that basically you can do that you can think about, from the finding minerals to the different valence states, major trace elements, and then isotopes too. So the logic is similar as all samples, natural samples we have been working on from the metal diamonds. The difference is that deep diamonds or diamond inclusion, they're very small. So it provides a challenge for different kinds of analytical instrument. Also, it becomes a challenge by getting the samples and finding the appropriate samples. So that's the tricky part for diamond research, as I'm thinking. Okay, with that, I think there's so much for reading today. Thanks, Lei, for leading the discussion. And thanks everyone for your participation and contribution. Have a good day and see you on Wednesday. Bye-bye.